2024 A-Level Combined Mathematics Paper 1, Part B, question number 14, Part A. Part B of the same question will be discussed in a future video, link in the top right. Part A of this question has to do with graphs and derivatives. The question says, let fx be equal to px plus q divided by x minus 1 times x minus 2 for x element of the real numbers minus a set of 1, 2. So basically every real number except for x equals 1 and x equals 2, where p and q themselves are also elements of the real numbers. It is given that the graph of y equals fx has a stationary point at 0, 1. Now this actually gives us two bits of information. The first one is, when we have x equals 0, the corresponding y value is y equals 1. And therefore, if we substitute into this equation, we can see 1 is equal to f of 0. Therefore, if we substitute f of 0, we're going to get 1. The second point is that, since this is a stationary point, we know that for this graph, when you take its derivative and you substitute in 0, you're going to get 0. Because for a stationary point to occur, in your graph, you need to have the derivative of the graph or the gradient of the tangent being equal to 0. And therefore, we can say the derivative is also going to be equal to 0 at the point 0, 1. Now, given this information, we are asked to show that p is equal to negative 3 and q is equal to 2. It then says, for these values of p and q, show that f prime x, the derivative of fx, is given by f prime x equal to x times 3x minus 4 divided by x minus 1 squared times x minus 2 squared, again for x not equal to 1 and 2. So basically every real number except for x equals 1 and x equals 2, and find the intervals on which fx is decreasing and the intervals on which fx is increasing. Now for that, we basically need to find the derivative, find when the derivative is positive and when it is negative. When the derivative is positive, it means that we are increasing, and when the derivative is negative, it means that we are decreasing. Now after that, they say, sketch the graph of y equals fx indicating the asymptotes and the turning points, and then hence find the number of real solutions to the equation x squared times x minus 1 times x minus 2 equal to 2 minus 3x. Now to start off with this question, the first thing we need to do is to use the fact that given this function, for x element of the real numbers except for 1 and 2 and pq element of the real numbers, we know that the graph y equals fx has a stationary point at 0, 1. Now we can go down and say, if y equals fx has a stationary point at 0, 1, we can derive two bits of information. The first one is, when y is equal to 1, fx is going to be f of 0. And therefore we have 1 equal f of 0. I'm going to call this equation A, which we'll be using to find p and q. Similarly, another thing we can say is that since it's a stationary point, f prime of 0 is going to be equal to 0. So basically, f of 0, or the value of f of x at x equals 0, is going to be equal to 1 since y is 1. And since it's a stationary point, the derivative f prime of 0 is going to be equal to 0, which I'm going to call equation B. Now we're going to be using equation A and equation B in order to find p and q. And since there's two simultaneous equations and two variables p and q, we'll be able to find them. Now considering this, we know that fx is equal to px plus q divided by x minus 1 times x minus 2 for x not equal to 1, 2 and p and q element of the real numbers. Given this, applying equation A, we can see from A, we're going to get on the left hand side a 1, and on the right hand side we get f of 0, which is going to be p times 0 plus q divided by, and inside the brackets we're going to get 0 minus 1, 0 minus 2. So basically minus 1 times minus 2, and on top we have p times 0 plus q. So here we can see the p times 0 just becomes 0, so we have q on top, divided by minus 1 times minus 2 is going to be plus 2, and therefore we get 1 equal to q divided by 2, leading us to q equals 2. Now we've already found one of the values. We've found that q is equal to 2. Now after that, in order to find p equals negative 3, we need to find f prime of 0 in order to use our second equation. Therefore, we'll now try to find f prime of x. So we'll try to find f prime x. Now as we know, if you have a function that is of the form f of x divided by g of x, or a quotient function, then we can use the quotient rule in order to find its derivative. If we have, let's say, f of x equal to g of x divided by h of x, then we know that the derivative f prime x is going to be equal to, from the quotient rule, g prime x hx minus gx h prime x divided by, and on the bottom we're going to have h of x squared. If you're interested in finding where this identity comes from, including the others that I'm going to be discussing in this video here, you can click this video at the top right. Now moving on, if we use this identity here, we can see, taking this, actually we'll put it in the side just so that we know where it came from. We'll make it a little bit smaller. We put it somewhere over here, so now we know where it comes from, and we can see, applying this identity here, f prime x we can see is equal to a function divided by another function. We have on top px plus q, which is now px plus 2, and on the bottom we have px plus q, and on the bottom we have x minus 1 times x minus 2. Now considering this, if we take x minus 1 times x minus 2 as one function and px plus q or px plus 2 as another function, we can see we can apply the rule that we have on the right side here into this function. Now considering that f prime x is going to be equal to g prime x here, which is going to be this function's derivative, which is going to be p plus 0, which is just p, since the derivative of px is going to be p and the derivative of 2 is 0, and therefore we just get p, times h of x, which is x minus 1, times x minus 2, minus g of x, which is px plus 2, times h prime of x, which is going to be the derivative of x minus 1 times x minus 2. Now considering this thing, of course, there's multiple different ways we can do this. I'm just going to do it the easy way. If we expand this bracket, we can see we're going to get x squared, and we're going to get minus 3x, and then plus 2. And we can see this is going to turn into 0. When we take the derivative of this part, we're going to get 2x minus 3. And therefore, the term here is 2x minus 3. Therefore, we're going to write h prime x, which is this part right here, this function, as 2x minus 3. And that's going to be divided by the denominator h of x function squared. Now in this case, we have x minus 1 times x minus 2. And therefore, that function squared is going to be equal to x minus 1 squared times x minus 2 squared. Now considering the answer they'd given us, they had already given us it in this form with x minus 1 squared on the bottom and x minus 2 squared on the bottom. So now we can be confident that we're actually on the right track. Now considering what we have, from equation b we can see if we substitute in x equals 0, we should get 0. Therefore, taking this equation, if we take equation b and we substitute, we can see we're going to get f prime of 0, which is going to be p times 0 minus 1 times 0 minus 2 minus p times 0 plus 2 times 2 times 0 minus 3 divided by 0 minus 1 squared times 0 minus 2 squared, which is going to be equal to 0. Now taking both sides down, we can see for the first part we have p times negative 1 times negative 2, which is going to be 2 times p. So therefore we have 2p, and then we have minus 0, p times 0 minus 2, but then we have this part right here, which is 0 minus 3, so negative 3 times negative 1 is going to be plus 3 times 2 is going to be plus 6, and therefore we have 2p plus 6 on top. On the bottom we can see we're going to get 0 minus 1 squared, which is 1 squared, which is going to be 1, times 0 minus 2 squared, which is going to be 0, or rather 2 squared, which is going to be equal to 4, and therefore we have divide by 4 here equals 0. Now rearranging, we can see if we take the 4 to the other side, we're going to get 2p plus 6 equals 0, leading us to p plus 3 equals 0, leading us to finally p equals negative 3. And hence we found p is equal to negative 3, we already found q is equal to 2, and we can see those two values are the values that we wanted to find in our original question. So therefore we can say finally p is equal to negative 3 and q is equal to 2. So we can say something like, therefore p equals negative 3, q equals 2, and we have found our values. Now finally, moving on to the next part of the question, we can see we need to use those two values in order to find f prime x. Now we already have found f prime x in terms of p and all of the other values. So therefore, all we need to do here is just substitute in p equals negative 3 into here. Now doing so, we can see we are going to get f prime x being equal to, and here we have negative 3 times x minus 1 times x minus 2. So we can write negative 3, x minus 1, x minus 2, and then we have minus, and then we have px plus 2, so negative 3x plus 2 times 2x minus 3. So negative 3x plus 2 times 2x minus 3, and then divided that by x minus 1 squared times x minus 2 squared. Now if we go up, we can see in their answer on the numerator they have x times 3x minus 4. Now we are going to do the same. We're going to take all of this and simplify it down, and we can see we're going to get minus 3x squared, and we're going to get x times negative 2, negative 1 times x, which is going to be negative 3x times negative 3, which is going to be positive 9x, and then we're going to get negative 3 times negative 1 times negative 2, which is going to be negative 6. And then we're going to get minus negative 3x times 2x, which is going to be minus is plus, so plus 6x squared, and then we're going to get minus 3x times minus 3, which is going to be plus 9x, 2x times 2x, which is going to be 2 times 2x, which is going to be 4x, so 4x plus 9x is 13x, and that minus is going to be minus 13x. And then finally we're going to have minus times plus 2 times minus 3, which is going to be plus 6, and therefore plus 6. Now here we can see if we divide that by x minus 1 squared and x minus 2 squared and simplify, we're going to get minus 3x squared plus 6x squared, which is going to be plus 3x squared, so plus 3x squared, and then plus 9x minus 13x is going to be minus 4x, so therefore we have minus 4x there. And finally we can see the minus 6 here and the plus 6 cancel, meaning there's no constant term on the top, and we just have that part of minus 4x divided by x minus 1 squared times x minus 2 squared. Now finally, factoring out an x here, we can see we're going to get x times 3x minus 4 divided by x minus 1 squared times x minus 2 squared. And that is our final answer for f prime x. So we can see here f prime x is in fact equal to x times 3x minus 4 divided by x minus 1 squared times x minus 2 squared. Now moving on to the next part, they say this is true for x not equal to 1 and 2, and we are asked to find the intervals on which fx is increasing and the intervals on which fx is decreasing. Now considering that, if we go down, we're going to write that this is for x not equal to 1 and 2. Now for f prime x, we can see on the bottom here we have negative x minus 1, which is going to be changing at the value of x equals 1. We're going to have x minus 2, which will be changing at the value of x equals 2. But on the numerator, we also have an x here, which is going to be changing signs when x is equal to 0, since on one side it's going to be positive and on the other side it's going to be negative. And we also have 3x minus 4, which is going to be changing when 3x minus 4 is equal to 0. So considering 3x minus 4 equals 0, this means that 3x is equal to 4, and therefore x is equal to 4 over 3. Therefore, at the x coordinate x equals 4 over 3, our derivative function f prime x is going to be changing signs. On one side of x equals 4 over 3, it's going to be positive, on the other side it's going to be negative. So here we can see we've identified 4 important values: x equals 0, x equals 4 over 3, and of course x equals 1, and x equals 2, and all of these we have to consider when we are considering the signs and therefore the increasing and decreasing regions of f of x. Now for this, the standard way that we would write this is using a kind of table. So we draw a table like this, and in this table we'd have 2 columns. The first column being the value of x that we're considering, or the range, and second we'd have a column that has just the value of f prime x at that point, considering whether it's going to be positive or negative. And if it's positive, we'll say the function is increasing, and if it's negative, we'll say the function is decreasing. So we'll draw a table like this with 3 rows, 1, 2, and 3. And in this case, since we have 4 points of interest, we're going to have 5 regions in between those 4 points up to infinity. So therefore, we're going to have 5 total columns here. We're going to have the first column, which is of course going to be the classifying what each of these rows is, and then we're going to have 5 columns: 1, 2, 3, 4, and 5. Now, the first column is going to be the range of x. The second column is going to be the sign of f prime x, since that's what we really care about when we are considering whether fx is increasing or decreasing. If f prime x is positive, fx is increasing, and if f prime x is negative, fx is decreasing. So then finally we can write, is fx increasing or decreasing? Is fx increasing or decreasing? Now, considering our values, we have x equals 1, x equals 2, x equals 0, and x equals 4 over 3. Out of those, the lowest value is x equals 0. And therefore, we'll consider first negative infinity up to that lowest value of x equals 0. Next, we'll consider the next range, which is going to be 0 until x equals, and the next value is going to be 1. Since 4 over 3 is greater than 1, 1 is going to be the lowest value that we are considering. So therefore, we need to consider until x equals 1. Next, we can consider from x equals 1 upward until the next value, which is going to be x equals 4 over 3, and finally 4 over 3 until the final goalpost of x equals 2, and then after that goalpost, we can go until x equals positive infinity. So these are the 5 ranges created by the 4 special values of x that are going to change the function f prime x, which are x equals 0, x equals 1, x equals 4 over 3, and x equals 2. Now, considering the first values, for the values of x in between negative infinity and 0, we can see x is going to be negative, 3x minus 4 is going to be negative, this is going to be negative but it's squared so it's positive, and this is going to be negative but it's squared so it's also positive. And therefore, what we have here is a negative number times a negative number divided by a negative number squared, which is a positive number, and another negative number squared, which is a positive number, which is going to be a positive number. The two negatives cancel out. These are two anyway positive, and therefore we get a positive number as our answer. Now, considering the next range, we can see we have to find in between x equals 0 and x equals 1. For this range, x is going to turn into positive. So therefore, this first term is positive. Now, the second term, 3x minus 4, however, is still negative, so we can write negative there. And the other two terms are also negative. So we have negative number squared and negative number squared, and we can see we have negative squared, which is going to anyway be positive. On top, we have a negative and a positive, which means if we multiply them together, we're going to get negative number, meaning that for this range, f prime x is negative. Now, for the next range, if we consider, we have 1 until 4 over 3. And for this range, since x is bigger than 1, x minus 1 is now going to be positive. However, this doesn't really change anything, because you can see if we substitute in, we have a positive number, a negative number for 3x minus 4, divided by positive number for x minus 1 squared and negative number for x minus 2 squared. Now this is positive, this is anyway positive, this is positive, and this is negative, which means that our sign is still negative. So this didn't change anything. Going from x in between 0 and 1 and 4 over 3 didn't actually change anything for the actual sign of f prime x. However, since the value at x equals 1 doesn't exist, we do need to make this break. Now, moving on from that, for the next value, if we consider x equals 4 over 3 and x equals 2, in between those two, 3x minus 4 is going to be positive. So therefore, we have a positive number in x, another positive value in 3x minus 4, divided by a positive value for x minus 1 squared and a negative value for x minus 2 also squared. Now this square is going to be positive, this is also positive, everything is positive, meaning the final answer is positive. Now for the last one, we have x's in between 2 and infinity, and for these values, every single term in all of 4 brackets is positive. So we have positive, positive, divided by positive, squared, and another positive squared. And we can see once again, if you substitute in these, you can see we get a positive number here, and therefore going from x equals to some values less than 2 and x equals values greater than 2 didn't actually do anything for the sign. However, of course, we still need to separate them. We cannot write x equals 2 in the middle, because of course for x equals 2, the function doesn't exist. It doesn't exist for x equals 1 and x equals 2. And with that, we have completed this part of the table and can now move on to stating whether fx is increasing or decreasing. Now for any graph, if you have a positive gradient, meaning you have something like this, it is going to be increasing. And for a positive gradient to occur, the derivative of the graph must be positive. So here we can see, since the derivative of prime x is positive for this range, and this range, the graph must be increasing for those ranges. So therefore we can write in these boxes here, increasing, here also increasing, and here also increasing. And to show that we know what increasing means, we could even draw an arrow like this to indicate we are going upward in the rightward direction, rightward up. Now considering the other two, we can see for this range and this range, we have negative values for f prime x, and therefore for those ranges, our graph is decreasing. So in those two boxes we can write decreasing with a downward arrow like this, and similarly decreasing with a downward arrow like this. And with that, we have completed our graph for this part, and now we are also expected to find the turning points and the stationary points in our graph, because they said in our sketch we need to indicate asymptotes and the turning points. Now considering this graph, we can find the turning points, and we can see them by the fact that in between x equals values less than 0 and x equals values greater than 0, we're going from increasing to decreasing, and also the graph exists at x equals 0. Due to this, we can see our graph is going up, 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 but then it soul turns around at x equals 0, it should stop, and it's going to go down again, meaning that for these values, we are going to have at x equals 0 a stationary point, which we can see, since we're going up before it and down after it, it is a local maximum. So we can say at x equals 0, and we can also write the corresponding y value, and we've actually given the y value in the question. They said for x equals 0, y is equal to 1, since 0 comma 1 is a point, and therefore we can say for x equals 0 comma y equals 1, we have, or we can say there is a local maximum stationary point. Now considering the other ranges, we can see we're decreasing and decreasing here, so there's no stationary point here. But for this range and this range, we can see we are decreasing and then increasing, and the function does in fact exist for x equals 4 over 3. And therefore this function is continuous, and it is going to be like this, going down, 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 turning around and then going up, up, up again, meaning we have down and up, resulting in a stationary point at x equals 4 over 3 that is going to be a local minimum. And therefore we can find at x equals 4 over 3 a local minimum. So we can say at x equals 4 over 3 and y equals, and we'll find the y later, there is a local minimum. Now considering the final one, we have increases and increases here and here, meaning that it's not possible for that to be a stationary point in between these two ranges. So with that, we're done with finding all of the stationary points and the turning points and calling them local minima or local maxima. Now in order to find the y-coordinate of this local minimum point, what we need to do is to substitute x equals 4 over 3 into f of x. Now going up, f of x is equal to px plus q divided by x minus 1 times x minus 2, where p is equal to negative 3 and q is equal to 2. Therefore, if we go down and substitute, we get f of x equal to negative 3x plus 2 divided by x minus 1 times x minus 2. Now considering this, if we substitute x equals 4 over 3, we're going to get f of 4 over 3, which is going to be equal to negative 3 times 4 over 3 plus 2 divided by 4 over 3 minus 1 times 4 over 3 minus 2. Now simplifying the numerator, we can see cutting this 3 and this 3, we get negative 4 plus 2 on top. On the bottom we can see we have 4 over 3 minus 1, which is 4 over 3 minus 3 over 3, which is going to be 1 over 3 times, and here we get 4 over 3 minus 2, which is 4 over 3 minus 6 over 3, which is going to be negative 2 over 3. Now simplifying, on the numerator we get negative 4 plus 2, which is negative 2, divided by, and on the bottom we get, if we multiply these two fractions, negative 2 over 9. Now cancelling out this negative 2 and this negative 2, we can see we are left with 1 over 9. Now 1 over 1 over 9 is going to be equal to 9, and therefore the final answer is 9, meaning that the y-coordinate corresponding to x equals 4 over 3 is also equal to 9. So with this, we have found the coordinates of our two local maximum and local minimums. The local maximum is at x equals 0 and y equals 1, and the local minimum is at x equals 4 over 3 and y equals 9. Now, other than these 2 points, we need a bit more information in order to find what we need in order to draw the graph, and the little bits of information that we need in addition to these 2 points are the vertical and horizontal asymptotes. Now, first we consider the vertical asymptotes. For this particular function, the only way that we can have a local vertical asymptote is if the denominator here is approaching 0. Because as the denominator approaches 0, we have some number divided by a very small number, which is going to be a very big number, which is going to blow up to infinity. Therefore, when the denominator approaches 0, we're going to have local vertical asymptotes. So considering this, the only way the denominator approaches 0 is if either x minus 1 approaches 0 or x minus 2 approaches 0. So due to that, we can see the only way the denominator approaches 0 and we get local vertical asymptotes is if x approaches 1 or x approaches 2. Now considering each of these, if we go to our graph, we can see as we get x approaches 1, from the left hand side, we're going to be decreasing. And due to that, if we have a vertical asymptote there, we're going to be decreasing until we go to negative infinity. Now similarly, considering the other side, for x's greater than 1 approaching 1, we can see as we go to the right hand side space, we're decreasing. We need to be starting from infinity and decreasing downward like this. So due to this, the shape of the asymptote at this point is going to be something like this. Going to negative infinity as we approach 1 from the negative side, and going down from positive infinity as we go away from 1 from the positive side. So we can see that this is going to be the shape of our asymptote at x equals 1. Now let's consider x equals 2. As we approach from the left hand side, we can see, since our graph is increasing, as we approach x equals 2, we're going to get a vertically upward increasing graph like this that goes to positive infinity as we approach x equals 2. Now considering the other side, on this side also, since we're increasing, we need to have started from negative infinity and be going upward. Now due to this, we can see the two vertical asymptotes are opposite in direction. The first one is decreasing and then going down like this, and the second one is increasing and then going up like this. These are the two shapes of the two vertical asymptotes that we're going to have in our graph. Now other than this, the other thing we need is the horizontal asymptote. Now in this particular case, for this graph, we can see, since this graph has order 1 on the numerator with px plus 2, but order 2 in the denominator with x minus 1 times x minus 2 in the denominator, we are going to have this graph approaching 0 as we take x to either positive or negative infinity. So due to that, we know that as we approach x equals positive infinity or negative infinity, our graph of x is going to approach 0. Due to that, we can see y equals 0 is going to be the horizontal asymptote of this graph. So with that, we know the two vertical asymptotes and the horizontal asymptotes. Now in the answer sheet, what we need to do is to indicate how we know this. So what we're going to do is to start with the first asymptote, which occurs at x equals 1, and we're going to approach x equals 1 from both the positive side and the negative side separately, consider what we get, and using that, draw asymptote, and similarly do the same thing for x approaches 2 from the positive and negative sides, and finally we're going to consider x approaches plus or minus infinity for the horizontal asymptote. So first off, what we're going to do is to consider limit as x approaches 1 from the positive side of f of x, and also the limit as x approaches 1 from the negative side of f of x, and similarly we're going to consider the limit as x approaches 2 from the positive side of f of x, and also the limit as x approaches 2 from the negative side of f of x. And finally, since we know that both plus and infinity and minus infinity are going to give the same thing, we can just say we're going to consider the limit as x approaches plus or minus infinity of f of x. Now this one we already know is equal to 0, since the denominator's order is greater than numerator. Now other than these ones, what we need to do is to consider these four, and if we go up to our diagram where we have all of our decreasing and increasing functions, we can see as we approach x from the positive side, x equals 1 rather from the positive side, which is this way, since as we go rightward is decreasing, as we go leftward is increasing to positive infinity. So therefore the answer here is plus infinity. Now for this one, as we know, since we approach one from negative direction where decreasing, we need to go to negative infinity, and therefore the answer here is negative infinity. Now similarly for x equals 2, since we know we're increasing on this side, we must be starting from negative infinity, and therefore for x equals 2, when we approach x equals 2 from the positive side, we're going to get a negative infinity instead. And similarly for this one, when we approach x equals 2 from the negative side, we can see we're increasing like this to positive infinity, and therefore our answer for this one is plus infinity. Now from these, we can draw the shapes of our asymptotes. From these two we know on the right hand side is approaching plus infinity, left hand side is minus infinity, and therefore the shape of the graph is going to be downward on the left hand side and upward like this on the right hand side at x equals 1. So we can draw a vertical line like this and say this is x equals 1. Now similarly for the second one, we can draw another one where in this time we have negative infinity on the right hand side and positive infinity on the left hand side. So therefore this graph is going to be like this, and we can draw the vertical line here at x equals 2. Now you don't need to draw this very big, you can just draw them a little small so that people understand, that you understand what these asymptotes are. So you can just draw this like this, little small. It's not that necessary, it's just that you need the limits. This is just going to be, for your visual understanding. You don't really need to draw this, but if you draw it, you'll be sure that the examiner also knows that you understand the concept. Now with this, we can finally start drawing our graphs. So considering all the information that we have, we know that our graph passes through the point 0, 1, and it's a local maximum at that point. And we also know our graph passes through the point 4, 3, and 9, and there's a local minimum at that point. We also know as we approach infinity, it is going to flatline at 0 from either direction. And we also know as we approach x equals 1, it's going to have to do this. As we approach x equals 2, it's going to have to do this. And we also know it is going to have this behavior in all of the other ranges. So now with that, we can start drawing our graph. So there we are. As you can see, I've drawn the graph, I've drawn the x-axis, the y-axis, and the origin. And additionally, I've also drawn some points on the y-axis and the x-axis that are going to be important for drawing our graph. The 2 points on the y-axis are y equals 1 and y equals 9, and these two are important because those two correspond to the local maximum and local minimum respectively of our graph. As you can see, y equals 1 is the coordinate of the local maximum and y equals 9 is the coordinate of the local minimum. Now similarly, the four coordinates x equals 0, x equals 1, x equals 4 over 3, and x equals 2 are important. X equals 1 and x equals 2 are important since those two are the two values at which we get our vertical asymptotes. Similarly, x equals 0 and x equals 4 over 3 are important since those two are the two x coordinates of our local maximum and local minimum respectively. Now with these points, we can start drawing our graph based on the derivative information that we have here. So I think I'm going to start from the left hand side, and considering the left hand side, I know that my horizontal asymptote is at y equals 0, and therefore I need to start at y equals 0 and either go up or down. Now considering the derivative graph, we can see on the range from negative infinity up to x equals 0, our graph is increasing, and after x equals 0, our graph is decreasing again. So due to this, I know I have to continuously increase from y equals 0 until the turning point that occurs at x equals 0, which is going to be x equals 0, y equals 1. I need to go up until this point, turn at this point, and start going down again. And I also know at x equals 1, I should be moving to negative infinity. So therefore, if I start drawing from the left hand side, we're going to have a graph that starts at a very low value, close to 0, continuously increases, maybe not that much, maybe we'll tone it down a little bit, maybe like this, until it stops at this point and starts going down like this, and it goes down very fast as we approach x equals 1. So maybe not that fast, maybe I can again, this is a little tricky process. Of course, you're using a pencil, so you can erase it and just try again. You need to try to make it so that it's continuously increasing until we get close to x equals 1, and then it starts decreasing, and it decreases all the way down to negative infinity, but never approaches it, never reaches it, always approaches it as we approach x equals 1 from the negative side. So that's going to be what we have for the left hand side, and now we can consider the next value, which is x equals 1 and beyond. So considering that, on the right hand side of x equals 1, we need to be coming down from negative infinity, or rather positive infinity, and we also need to be continuously decreasing until we get to x equals 4 over 3, at which point we start increasing, meaning we have a local minimum at that point. So we can see we have to go down from positive infinity like this until we reach this point right here, which is the point x equals 4 over 3, y equals 9. We return at this point and start going upward, and as we go upward, we need to approach positive infinity at x equals 2. So therefore the graph here is going to be downward from positive infinity, turn at this point, upward again to positive infinity as we approach x equals 2. Now finally we can consider what's there to the right side of x equals 2. So for that, if we look at the diagram, we can see on the derivative graph, we have an increasing graph over here, and we can also see we are going to have to start coming from negative infinity onward, and we also know as we approach x equals positive infinity, we need to approach y equals 0. So combining all of this information, we know we need to have something that looks like this. Coming from negative infinity upward, 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 never passing the x-axis, and approaching y equals 0 as x approaches positive infinity. So therefore our graph is going to look something like this. Now it doesn't need to be exact, it just needs to have the same shape, because of course it is difficult to draw scale diagrams during the exam. So you can make this 9 very close to the 1, maybe somewhere here, you can do all of that. You can make this difference of 0 and 1 very big, so that you can easily draw this curve, all of that. But in my case, I decided to make it realistic, so that it looks very similar to what you would actually get. And here I'll flash a quick image of the actual graph of f of x real quick, so that you can see the actual image, but it does look very similar to this. So now here the only additional thing we need to do here is to mark the horizontal and vertical asymptotes. So here on the x-axis I'm going to mark horizontal asymptote. I'm going to say horizontal asymptote at y equals 0. I'm going to do the same thing over here. I'm going to say horizontal asymptote at y equals 0, and we're going to do the same thing for the vertical asymptotes. Here I'm going to mark vertical asymptote at, and in this case this one's at x equals 1, and the other one is going to be vertical asymptote, vertical asymptote, and this one's at x equals 2. And that is going to be all for this graph. We can see we've already marked the local maxima and local minima with this point, and with that we are done for the graph. Now the final part of the question says, hence find the number of real solutions to the equation x squared times x minus 1 times x minus 2 equals 2 minus 3x. Now this might look a little bit familiar to you, since if you consider this equation, we can see minus 3x plus 2 divided by x minus 1 times x minus 2 is in fact exactly what f of x is. And you'll be right with that, because this is what we need to use in order to find the number of real solutions for this equation right here. So what we're going to do is to go down and consider that equation and rearrange it to get it in terms of f of x. So going down, we have x squared times x minus 1 times x minus 2 equal to 2 minus 3x. We're going to divide both sides by x minus 1 times x minus 2 and write this as x squared equal to minus 3x plus 2 divided by x minus 1 times x minus 2. And as we know, this thing right here is exactly what f of x is. This is exactly equal to f of x. And therefore what we're looking for is f of x equal to x squared. Now we can solve this very easily by simply using the graph that we have above, and what we're going to do is to draw the graph of y equals x squared in the same diagram that we draw in the graph of y equals f of x. Now with that we can see the points at which f of x is equal to x squared are going to be represented by all of the intersection points of y equals f of x and y equals x squared. Therefore going up we can see if we draw y equals x squared, which is going to look something like this, we can count the number of intersections and say that that number is exactly equal to the number of total real solutions for this equation that we had at the start here. Now going up, if we consider drawing the graph of y equals x squared is of course going to go through the origin, and it's going to go up on this side and up on this side as well. So therefore it's going to look something like this. Now we need to be a little careful, since it is possible that this graph intersects this graph if its coefficients were different. But in this particular case, the graph of y equals x squared actually doesn't intersect the other graph here, this part of the graph. It actually directly goes up to infinity without ever touching this part of the graph here. But we need to make sure. And we can make sure of that by considering x equals 2 and the y value here. Now considering x equals 2, since this is y equals x squared, the corresponding y value is going to be y equals 4. And therefore every other value here is going to be less than y equals 4, and none of them are ever going to reach y equals 9, and therefore these two graphs will never intersect. Due to this, if we consider this graph here, which is the graph of y equals x squared, we can see this graph and the graph of y equals f of x intersect at only 2 points. They are this point right here and this point right here. So as we can see, since the graph, we can say something like, since y equals fx and y equals x squared intersect at only 2 points as shown above, there are only 2 solutions for the given equation. And with that, our question is completed. Now finally, let's discuss the marks awarded for this part of the question. So at the start of the question, when you use the fact that f of 0 is going to be equal to 1 and you substitute into f of x and find that q equals 2, finding q equals 2 gets you 5 marks. Now after this, when you find f prime x, the derivative of f of x, and you write down using the quotient rule this equation of f prime x like this, that directly gets you 10 marks. Now then, when you use the fact that f prime of 0 must be equal to 0 and you substitute in f of 0 and say that equal to 0, writing down this substitution gets you 5 marks. Now after this simplifying down, when you eventually get that p is equal to negative 3, that gets you another 5 marks. Now taking these two values, p equals negative 3 and q equals 2, and resubstituting them into the expression for f prime x like this gets you another 5 marks. Simplifying that down and getting the final expression given in the question, which is x times 3x minus 4 divided by x minus 1 squared times x minus 2 squared like this, gets you another 5 marks. After that, when you construct the table, for each of the 5 different ranges from negative infinity to 0, 0 to 1, 1 to 4 on 3, 4 on 3 to 2, and 2 all the way up to positive infinity, for all 5 ranges, when you get each of the signs of the derivative correct, like this, you get 5 marks for each range. 5 for this, 5 for this, 5 for this, 5 for this, and 5 for this. Now after that, when you state that they are increasing or decreasing, getting all increasing and decreasings correct gets you a total of 10 marks for getting everything correct. Now after this, for the 2 turning points, when you identify that the 2 coordinates at which the 2 turning points occur are x equals 0 and x equals 4 over 3, that gets you 5 marks. After this, when you write down the 2 coordinates and say that the first one, x equals 0, y equals 1, is a local maximum, and the other one, x equals 4 over 3, y equals 9, is a local minimum, you get 5 marks for each of them. Now after the local minima and maxima, when you then move on to the asymptotes, for finding the 2 vertical asymptotes like this, both of them get you 5 marks, and for finding the horizontal asymptote, you get another 5 marks. Now using all of this information, when you then go down and draw the graph, for the first part of the graph that is there in values of x less than x equals 1, getting the shape correct and all the points correct gets you 5 marks. After that, for the values of x in between 1 and 2, drawing the graph with the shape correct and all the points correct gets you another 5 marks. And finally, for all the values of x greater than 2, when you draw the graph correctly with the correct shape and draw it as it's approaching x equals, or rather y equals 0, and as it approaches x equals 2, approaches negative infinity, when you draw all that correctly, you get another 5 marks for that. And finally, when you say that this equation is equivalent to finding f of x equals x squared like this, you get 5 marks. And finally, when you draw the graph of y equals f of x, or rather y equals x squared, in the graph of y equals f of x, and you find that there are 2 intersection points, and you say that therefore the total number of solutions is 2, that gets you another final 5 marks. And that is going to be all for this question. So I hope you enjoyed. If you have any feedback, post them in the comments down below. Thank you for watching, and goodbye.